Hi, in this video I'll demonstrate how to calculate the Mann-Whitney U test using a formula. Of course, we can calculate the same values using SPSS, but when you use the formula you get a better understanding of what it actually does. So I'll show you both. I'll show you how to do this using formula and using SPSS. The example that I'm going to use comes from Siegel's book from 1956, Non-Parametric Statistics for the Behavioral Sciences. It's an oldie but a goodie. It's kind of considered a classic text in the field of non-parametric stats. And I like it because he gives very clear examples. The data down here come from one of Siegel's examples. So we've got two groups, an experimental group that has 3 scores in it, and a control group that has 4 scores in it. And you can see that what I've done down here is I've arranged the scores in sequence from lowest to highest, keeping track of which group they're in. So the C in parentheses stands for control group, the E in parentheses stands for experimental group. Now, in order to calculate the U statistic, there are actually going to be 2 different ones. There's one that you have a U statistic for the experimental group as well as a U statistic for the control group. We only are interested in the lower U statistic value. Whichever one is the lowest is the one that's actually used to determine the probability that the events are not random, that the rankings are not equivalent in the 2 groups. The whole approach here is to judge whether or not it looks like the rankings themselves are randomly distributed, and so you're looking to see if you have about the same amount of rank on one group as in the other. So here's how we do it. In order to get the U statistic for the experimental group, what you do is you look at the position of the first control group score. That's the first control group score is 6. How many experimental group scores are in front of that on the left side? There are none. So we enter a 0 right here. We go to the second control group score, that's 8. How many experimental group scores are in front of that? There are 0. So we enter that here. The next control group score is 10. That's this one here. How many experimental group scores are in front of that one? There's 1. The square of 9. So we get a value of 1 here. And then the next and last control group value in the series is 13. How many experimental group scores fall in front of that? Well, you have 1 here, that's an 11. And you also have this one that we already counted. We count it again. We get to count it again. So for the control group score of 13, there are 2 values in the experimental group that are in front of it. And that's where the 2 goes, right here. So the U statistic comes out to be 3 for the experimental group. That's that. And we can calculate using the same procedure for the control group. Going to the first experimental group score, how many control group scores are in front of it? There are 2, 6 and 8. So that 2 goes down here. For the next experimental group score, that's 11. How many control group scores are in front of it? There are 3. That goes here. And for the last experimental group score, how many control group scores are in front of it? There are 4. So that goes right here. Now we have a U statistic for the control group, which is equal to 9. So we have 3 for the experimental group and 9 for the control group. We only use the smaller one for the U statistic. And let's see how SPSS handles it. So I'm going to pop over to SPSS. You can see that I've got it set up already. I just have my groups labeled by number. I didn't put the names in. Group 1 and Group 2. we go back to the document, we can see that group 1 is the experimental group, group 2 is the control group. I've got my scores entered here. And to analyze it, we go to Analyze Non-Parametric Legacy, 2 independent samples. 2 independent samples. I'll reset it to start from scratch. Group goes into grouping variable, and whenever you see the question marks in SPSS, what that does is it tells you that you have to click this button to define the groups, just like you do with an independent samples t-test. You just put the numbers that correspond to the different groups you're looking at, 1 and 2. Then our dependent variable goes up here, and you can see that the Mann-Whitney test is checked already. It does that by default, so we don't have to actually do anything. There is nothing extra in the options, so we'll go ahead and run it, and you can see down here in the output that we have the Mann-Whitney U statistic of 3. It doesn't give us the other group. It doesn't give us 9. But it does give us a z-test. I'll talk about that in a minute. So it only uses the lower value. Okay. Now, that approach works fine if you have a small sample, but what if you have a large sample? It gets really, really tedious to count up all those preceding control group or experimental group values. And so there's a formula, and the formula is pretty easy to use. You've got it right here. The N1 and N2 referring to the number of observations in group 1, group 2, and R, which is the sum of the ranks. And this is the formula when you do not have ties. So let's see how this works. Using the same set of data from Siegel, we arrange the values and we assign the ranks based on the lowest score. The lowest score is 6. That gets a value of 1. The next lower score is 8. That gets a value of 2. The next lower score is 9. See, we have to switch over to the experimental group. That gets the next rank of 3. Then the next rank, or the next higher score, is 10, and that gets a rank of 4. And so once you've assigned all the ranks, if you have 7 scores, you're going to have 7 ranks. Once you get all the ranks, then you can get the sum of the ranks. So the sum of the ranks for the control group is 13. Sum of the ranks for the experimental group is 15. Now let's see how the formula works. So I'm going to do this for both of the groups, for the control group and the experimental. And you can see here that the n of the control group is 4, the n of the experimental group is 3. So following the formula, 4 times 3 plus, and then we have this fraction, 4 times 4 plus 1 divided by 2 minus the sum of the ranks for the control group. So that's where this 13 comes from, right here. And then when you do the simple arithmetic, you get the U statistic for the control group is 9. And we do the same thing over here with the experimental group. The number in the experimental group is different. It's 3 instead of 4, so we have a smaller number here. And we have a larger number for the ranks. And in combination, that results in our smaller U statistic. And those match the computations on the previous page. When we were just looking at the arrangement here, I calculated 3 and 9. And we have 3 and 9. Well, what happens when you have ties? ties make things a little bit more complicated, and the formula will not be exact. So let's see how that works. In order to demonstrate this one with ties, I'm going to use a set of data from Parker, Van Ness, Davis, and Sauber in their 2011 article, where they discuss the development of a brand new statistic that they call the tau U statistic. And they talk about how it relates to the Mann-Whitney U, although not in very clear terms, I might add. I'll have something to say about that in a different video. But for our demonstration, it works well. So these are the data from the Parker and colleagues article. You have two phases, treatment phase, or rather control phase, which is phase A, and then a treatment phase, phase B. And you can see that we do have some ties. We've got a couple of values of 3 here, and we've got a couple of values of 5 over here and another 5 over here. So we've got 2 ties. The first tie has 2 values that are tied, and the second tie has 3 values that are tied. So that's going to make things a little bit complicated. So we have a total of 9 scores, so there are going to be 9 ranks. And when you have tied scores, you use up the ranks. So let's say this one is rank 1. Well, 3, we have 2 values of 3, which is the next higher number. And so this is going to take up both rank number 2 and rank number 3. So basically what we do in order to deal with these tied scores is they share the rankings of rank 2 and rank 3. In order to deal with that, what we do is we take the average of those ranks. So rank 2 plus rank 3 equals 5. We divide that by 2, which is the number of ties. The number of ties is 2. So both of these scores of 3 will receive the rank of 2.5. And I go through all the different allotments of ranks here. The score of 2 receives a rank of 1. The score of 3 is tied and it appears twice. We take rank 2 and rank 3, take the average of that, which is 2.5. Both of those values of 3 get the rank of 2.5, and then the next possible rank in the sequence is going to be rank 4, because ranks 2 and 3 were used up in this current step. Next, the score of 4 receives a rank of 4. The score of 5 appears 3 times and uses up 3 ranks, rank 5, 6, and 7. We take the average of 5, 6, and 7, which is 6. So each time the score of 5 shows up, it gets the rank of 6, and then the next available rank in the sequence is going to be rank 8. So ultimately, what you get is something that looks like this. You can see where the ties are. Here's the 3 and the 3. They both get a rank of 2.5. And we have 2 5s over here and another 5 over here. And they all get the rank of 6. And ultimately you see that the highest or greatest value of a rank is 9. That's because there are 9 scores. So you have to have an equal number of ranks according to the number of scores that you have, but not every rank shows up. Like the rank 5 and rank 7 do not appear here because we're using the average of those ties, which comes out to be rank 6, if that makes sense. Then you sum up the ranks, plug those into the formula, and calculate it the same way that I did in the past. And again, this is the formula without the correction for ties. It's going to give us the wrong answer, but I want to show you how that works. So the values for U are correct. The U statistic is correct. If we plug this into SPSS, it'll tell us that the U statistic is 2. But the Z score that we get is not correct. Here's the formula for the z-score without correction for ties. This would work if we had data with no ties, but since we have ties, it's going to give us a slightly different value. So we take the values. The u that we use is the smallest one, which is 2. See, we had the choice between 2 and 18. So the u that we use here is the smallest one, which is 2. And then we have the n for the two groups. The first group has 4, the second group has 5. 2 minus 4 times 5 divided by 2. So that's 20 divided by 2 is 10. 2 minus 10 is negative 8. And then in the denominator, we have the sample size of the first group, sample size of the second group. We have a little bit of order of operations and arithmetic here. Divide by 12 and then take the root. And ultimately you get the answer of negative 1.959. Let's call it negative 1.96. Now SPSS, I don't have it set up, so I'm not going to run it, but I've already run it. And SPSS gives us the value of z equals negative 2.002. And I was very precise, as you can see, going out to many decimal points. So the difference here is not rounding error. And we always want to know that we're getting the same thing that SPSS does, so that we know that we've done it right. Conover, another non-parametric stats author with another classic text in 1999, at page 273, has an alternative formula, but a less clear example how to actually use it. So you can use that source as well, but it's not as easy to follow. This formula for the version with ties is from Siegel's 1956 book. So the Mann-Whitney formula with correction for ties, you can see that it does change the arrangement here, and we've got this unique addition to the formula, which is the sum of t, where t equals, capital T equals lowercase t cubed minus t divided by 12. And t is the number of tied observations for a given rank. So I'll show you how to do this. It's actually not that hard. So we'll continue with the example provided by Parker and his colleagues in the 2011 article for the tau u statistic. And I've highlighted the ties here. The first tie has 2 values. The second tie has 3 values that are tied. These are the rankings of the ties. So we have 2 values of 3, the actual scores, 2 raw score values of 3 that were tied. Their ranking is 2.5. And we have 3 values of 5 that are tied, and their ranking is 6. So first, what we want to do is we want to compute the sum of capital T. And it works like this. Take t cubed, which is the number of ties. The first one has 2 ties, so the t here is 2, the lowercase t is 2. So it's 2 cubed minus 2 divided by 12, which is 0.5. And then for the second tie, which is the value, the raw score values of 5, where we have the ranking of 6. We've got 3 values that are tied. So what we're doing is we're counting the number of values that are tied. There are 3. 3 cubed minus 3 divided by 12 is 2. So the sum of capital T in this formula is 2.5. Now we can plug it into the larger formula. Everything else is simple arithmetic, just the sample sizes and the U statistic. Plug everything in, compute it out, and you get 2.002, which is exactly the same thing that SPSS gave us. So now we know how to compute the U statistic using the formula for this. When you compute the U statistic, the one that we use for reporting purposes is always the lower value. We never use the upper value. So it actually can be kind of confusing when people refer to the upper value for U, as Parker did in his 2011 article. I had to go back and look up, well, how do I get that value, because SPSS doesn't give it to me. Well, you just do it for each group using this formula. That's how you get the lower and upper values for the U statistic. And then the Z-score for the U statistic, we've got two. The one without ties, which is this one right here, and that gives you an inexact Z-score. And the one with ties, which is right here, where you have to go through the extra step of computing the sum of T, the sum of capital T, which involves taking the number of ties cubed minus the number of ties divided by 12. And when you do all that, then you have exactly the same Z-score that SPSS gives you, which is, it's a cool thing. And whenever I do any kind of a statistical analysis, I always like to be able to do it by hand using the formula so that I understand exactly what it is that's going on. And what the U statistic is doing here, it's telling you whether or not that that lower value for U, whether this seems to be random or not, based on the rankings. The rankings here are too small. The rankings for this U statistic, value of 2, are too small to have been conceivably occurring by chance. According to the Z test, the critical value for Z, of course, on a two-tailed test with alpha 0.05 is 1.96. This is greater than 1.96, so we reject the null hypothesis that we have an equivalent amount of rank for both the experimental and control group. So that's the U test. Thanks for watching. Hope that was helpful.